Recording now. All right, so welcome everyone who's watching the recording. And we just established that we're doing 5.5, 5.6, and the focus on theory. Are there any questions? Like, is there something that you would like us to focus on more so than other stuff? Like, I don't know. I mean, I can just kind of start from the beginning, but conceptually, I remember when I was learning this, I had a little bit of a problem just like trying to figure out like what all this like specifically was going on. And so if there's like questions that you have, please feel free to ask. Starting from the beginning is good? Okay. All right, so you guys do the odd problems. No, you guys do the odd problems. So let's do even problems this time around. Okay, so starting in 5.5. Where did my thing go? Okay. So this is talking about total change in the fundamental theorem of calculus. So let's just start at number 2 and see what we're doing. So if the marginal cost function, C prime of Q, oh, this is on page 270, by the way. So if the marginal cost function C prime of Q is measured in dollars per ton, and Q gives the quantity in tons, what are the units of measurement for this? And what does it represent? So go ahead and just kind of like put some of your thoughts in the chat box. Like, I just want to hear what you guys like. What is the first thing you guys think of when you start this problem? Okay, units is dollars. That's right. Okay, so let's write that down. What does this phrase then represent? This. So the change is 100. Okay, that is correct. We are going from 800 to 900. So this is a change over, let's see, how do I want to say this? A change over a distance of 100 units. In this case, the units would be, what would the units be in this instance? Tons. Yep. So we're going from 800 tons to 900 tons. And so this integral is expressing basically what that would be. So if I go from 800 tons to all of a sudden I'm making 900 tons. What is that going to do to my price? Or cost, not price, but cost. So basically what's happening here is they gave us something in C prime And, well, we don't necessarily know that. I mean, like, that's a logical thing. Or somebody said like increase. So yeah, but all we have is this very generic C prime. So C prime could mean the cost would increase. C prime could mean the cost would decrease. It's just like, it depends on what C prime is. But yeah, it, like, in the context that we're looking at, it would probably be an increase. But right now, this is just a generic equation. We don't know anything about it. But what we do know is that the integral of this thing, the integral of a derivative, is going to be the original function. So it's going to be C of Q. So this is going to be in dollars, and it is going to tell us when we're going from 800 to 900, it's telling us the change in cost the change in cost that's going to occur over a distance of 800 to 900. So let me erase a little bit of this. We're still going to talk about question 2. So say I have this sort of like a graph thing, and here is 800 units, and here is 900 units, and here is, we're going to assume an increase in cost as tons increase. This is based on logic, not the equation. Okay? So here we have some number, and here we have some larger number, and we have a scale that goes up that direction. So I'm going to draw C. So what is my function C of Q going to look like? Or am I drawing C, or am I drawing, I lied, I'm drawing C prime. So this is the marginal cost. Well, we know that we're assuming that there's an increase in cost as the tons increase, so it's going to be something with like a generally like positive slope. So it's just going to like go up. And that's all we like know from this. What I'm trying to get at is the graphical representation of the integral. So when I am trying to find from 800 to 900, the integral of C prime of Q, what's this going to look like? Well, this kind of refers back to exactly like what is an integral? Like in terms of, we have our algebraic definitions, and we have our graphical definitions of what's going on here. And the algebra is this integral sign, and the graphical representation of an integral is going to be it's going to be the area under the curve. So this is our definite integral. So most of this is just kind of like hypothetical. I just want you guys to like continuously relate area under curve to the integral. Okay. All right. So all right, let's try number 4. This is still on page 270. 270. So the population of Tokyo grew at a rate shown in figure 5.65. Estimate the change in population between 1970 and 1990. Okay, there are a few things that are kind of like buzzwords in this problem. First of all, the population grew at a rate that is like described by this graph. So we have this graph, and it's just this line, and it's got a positive slope. So this is the population growing at a rate. That means that this is the rate, of change. So that is going to be the derivative of the population. Which is why they call this P prime of t and not P of t. So this line represents the rate of change of the population. Here we have 1970. Here we have 1990. Let's see. So we're going to assume it starts here at 0. This is just above 0.3. And my scale is a little off here because I exaggerated this. And this is like 0.45. So my scale obviously is bad, but it's just kind of a sketch of something that is in your book. So I'm going to kind of leave it. Okay, so we are trying to find the change in the population between 1970 and 1990. What are we going to do? Well, we've been talking about integrals, so I hope you guys start thinking that we need to find the integral of P of t, or P prime of t, between 1990 and 1970. But another way to analyze this is the units, because if your units aren't lining up, then there's something wrong. So this is measured in, this is year, and this is rate of growth. So I'm just going to say rate of change. And so this is in millions per year, and this is in years. So we know that this line, this rate of change, is in millions per year. What happens if we take the integral of millions per year? We're going to end up with millions of people. So, which is population, which is what we want from this problem, because we want the change in population. Okay, so there are a couple ways to like check your answer as you're going through here. If you're not entirely sure like what you're supposed to be taking the integral of, in this case, I think it's fairly straightforward. Oh, you don't know how I got that. The units, or what don't you know how I got? Okay, is that kind of like the formula that you've been using to, oh, it's not times millions. So the rate of change of P of t, so P of t, or P prime of t, is going to be millions per year, because we're graphing the rate of, okay, so that's not like the unit, okay. Let's take a quick look at these units again. So this is graphing. So if we were to like pick this point in the year 1970, the rate of change depends, according to this function, the rate of change of the population depends on the year. And so we know this rate of change is measured in millions per year. So this graph is in the units of millions per year, or millions per year, because that's like what we're discussing here. if I were to graph P of t, not P prime of t, but P of t, it would look something like this. It would be continuously positive slope from that area. So that's a rate of change. This is a derivative. So what we're doing is we're taking a derivative and we're trying to graph the original function. And I am always bad at this. This is just not my strong suit. But I think it's going to look something like that. Nope, that's not how it's going to look. It's going to get more and more positive, not less and less positive. Oh, sorry, I remember when we were doing this graphing stuff and I told you that this was just like not my strongest suit. It's really not. So P of t is going to be continuously increasing. So it's positive and it's going to get more and more positive. So it's going to look something like that. So let's say that is 1970 and this is 1990. Okay. So this is also in years and this is millions of people. Right? Does this make sense? In terms of like what these units are. I like don't want to go on if, yeah, okay. So we're going to compare, sorry, I'm going to move the chat really quick. So we are going to compare what's going on in this purple graph, which is P prime of t, which is represented by rate of change per year. And what's going on in this pink graph, which is P of t, which is going to be millions of people per year. Does that make sense? So what we're really not we're not really considering this last year here because this is going to be the same regardless. Because what we're doing, if we take the derivative of this, it's going to be d dt of P of t. So we always are going to have this time on x-axis, on the x-axis. So this is going to be dp dt or P prime of t, right? So this time is always going to be on the x-axis. So we don't really want to like think about that in terms of like what units we're going to be working with right now. So that's like not my priority because that per year is always going to be there no matter how many derivatives or integrals we take because this axis is how we like measure things. So basically we're looking at the rate of change. So P prime of t is going to be represented by the rate of change and P of t is going to be represented by like, so this is millions per year. And this is going to be in millions and just millions because we're not really considering this time that's always going to be there because it just makes things really complicated. And okay, and that makes sense when you're thinking about like the graph as a whole. So when you're thinking about this whole thing, you're like, okay, so I have to think about how it's changing with regards to years. But when I'm just thinking about the population, like what is the population? If I'm thinking about like points on the graph, I have a fixed time. So I'm just going to think about it in terms of millions. Okay. So that is something to consider when you're solving problems like this, is that you just want to make sure that your units are in the right place. So I know that my units are in the right place because if I were to take an integral of P of t, I would end up with millions as my unit. And because consider integral, here is my P prime of t dt. This is in the units millions per year. So we're just taking this to be rate of change. This is in the units year. So you're gonna like multiply them together. This is not like actually how it works, but it's like a good way of like thinking about it. So the integral units will be millions. Okay. Are we on the same page? Yes, no, maybe so. Okay. Casey, I just want to make sure that I cleared that up and did not make it more confusing. Okay. All right. Okay, so we want to estimate the change in population between this time. So we have this change in population between 1970 and 1990, and we know that we want to find the integral of p prime of t, which is given in a graph. So what are we going to do? And look at the area under the curve. That's a really sloppy looking A. I don't need to write that down. It's the area under the curve. So I would break it into boxes. Boxes in this graph have units of, so let's see, that's 1975, 1980, 1985, 1990. So the graph is marked down by every 5 years. So like that's 5 years. And when you go up, it is 0.1 mil per year as a rate of change. So each box is going to represent 0.5 million. Of the boxes I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Let's say that's approximately 14 and 15. So I'm going to say I have approximately 15 boxes. So I have 7.5 million people. So from 1970 to 1990, according to this graph, the change in population was an additional 7.5 million people. I think the book says 7.65, but this is approximate. I go back up. Are we good? Cool. And it makes sense because it's in millions of people, and that's what we expected this to be in. So if we were to like have some sort of a curve that looks something like that, the distance between 1970 and 1990 would be, this isn't 0, but so we have a little line here. So this starts at something, and then from here, it's going to be a distance of 7.5, and it's in millions. But so that makes sense. Cool. That's kind of referring back to the actual fundamental theorem of calculus, which I hope we'll be able to get to. Where is it? Water. That's in rates. That's in. Did you guys do optimization? So I'm trying to find a good problem. I'm trying to find something that like does a really good job of demonstrating the fundamental theorem of calculus. Is there a problem that you guys tried to do from the suggested problems that you had a tough time with? Maybe? Five. So a marginal cost function, C prime of Q, is given in the figure below. If the fixed costs are $10,000, estimate the total cost to produce 30 units, the additional cost if the company increases production from 30 units to 40 units, and the value of C prime of 25. So
Olivia, sorry, I don't mean to cut you. I thought you were talking about fundamental, the part in the back.
Okay.
Focus on theory part, sorry. But
yeah.
So I was...
That's good.
All right, question 1, I kept getting the wrong answer. Like, it was off a bit. So that one was my tough one, if you want to do question 1.
So question 1, and then you also had problems with question 5 on this page?
No, I was okay with 5.
Okay.
Oh, on that page, on 289.
Yeah, on 289.
Okay.
Okay. Okie dokies. So we are going to flip to the focus on theory.
I don't know if I confused you, but I was talking about question 1 in section 5.5 and then question 5 in the focus on theory part.
Okay.
Okay.
All right, we will talk about the... Let's talk about the one in 5.5 first. And then let's talk about the focus on theory, okay? Okay, so we are in section 5.5 still. Ignore what I just wrote on there. We are going to be...
I don't mind going through, and then when we get to focus on theory, we can talk about 5.
Okay.
All right.
Okay, let me... Oh, lost my page. Okay. So a cup of coffee at 90 degrees Celsius is put in a 20 degrees Celsius room when T is equal to 0. The coffee's temperature is changing at a rate of R of T is equal to that equation, degrees Celsius per minute with T in minutes. Estimate the coffee's temperature when T is equal to 10. Okay, so this is still on page 270. This is going to be problem 1. We have this function. And I know that the units of R of T are equal to degrees Celsius per minute. Okay, so what I would do when starting at this problem, I would start by saying, what do I want? So what is it that this question is asking of me? Well, reading the question again, it says that I want the coffee's temperature given T. Yeah. So what do I have? Well, I have the temperature, or the time is, excuse me, is equal to 10. I have the equation for R of T, which is in degrees Celsius per minute, which is a rate of change. And okay, so I could theoretically graph R of T. So that is like one, perhaps, method of solving this problem. However, the easiest way of doing this would be to, okay, give me a hot sec. Where did it go? Where did it go? Where did it go? Okay, here we are. Okay. The easiest way to solve this would be using the fundamental theorem of calculus. Okay, so go ahead and tell me, like, in the chat box in like your own words, like what you think of the fundamental theorem of calculus. Like, how am I going to use that to help me solve this problem? Do you guys have any ideas? All right, let's start by putting in what the fundamental theorem is. So the fundamental theorem is that the definite integral f prime of t dt is equal to f of b minus f of a. Does this make sense? I want to make sure that you are on board with the fundamental theorem before anything else happens. Okay, good. So this equation is something that we're given. And we know that since this is a rate of change, if I were to take the derivative, or not derivative, excuse me, the integral of r of t, that I would end up with something in units c, degree c. Correct? Are we on board with that? Because this would be r of t dt. Cool. So I also have starting temp. Coffee. This is coffee, right? Yep. Which I know to be 90 degrees C. Okay. So let's take a look at these units. This is going to be in Celsius, this is going to be in Celsius, and this is going to be in Celsius. So that all makes sense, because if you have two things in degrees Celsius, then you're going to end up with something in degrees Celsius, correct? Okay, so all the units here are going to make sense. We can do what we will with them. So I want from time 0 to time 10 r of t dt. What is my issue here? Well, this would be equal to this. Which is something that you will be able to solve eventually, but right now that is, like, it's just not something that you can, I believe, right? I guess, did you guys talk about finding antiderivatives and that stuff? I think that might have been the stuff that we skipped last week. Oh, you did, okay. All right, so you tell me how to solve this then. So we can take this derivative, or what we can do is we can say, well, and what we can do is say that this is the case, and do we know what these are? Well, we know that, okay, let's rewrite some of this stuff. Sorry, I'm trying to, like, yes, f of a is going to be equal to 90. That's right. So we know things that we know. So we have this equation here. So we can say that the derivative from 0 to 10 is -7, 0.9 t dt is equal to f of 10 minus f of 0. And we know that f of 0 is equal to 90 degrees Celsius. And what is it that we want? We want the temperature given time equals t, which is f of 10. So this is what we want. So let's rearrange this equation to give us what we want. Let's add f of 0 to both sides. So we end up with the equation, that's 10, I'm just going to write RT here, dt is equal to, oh, excuse me, plus, so this is a phrase, f of 0 is equal to f of 10. So this is what we want. Now we have an equation that gives us what we want, correct? That's what we wanted. That's how we get to what we need. Okay, some things to notice. This is going to be 90 degrees. So this is going to be from 0 to 10 r of t dt plus 90 is equal to f of 10. We expect f of 10 to be what? Higher in temperature or lower in temperature? Lower. That's exactly right. What does that say about this integral? This integral is going to be negative, exactly, because we're adding 90 to it. Okay, so I am going to clear away some of this stuff and put what we have right now. So we have from 0 to 10, we have the equation negative 7 t dt, and that's equal to, minus plus is what we need. 90 is equal to f of 10, which is what we want. So let's solve it. How are we going to end up solving this? No ideas? The first thing I would do is pull that negative 7 out of there because I don't want it to bother me. Give me a sec. Okay, I'm trying to like figure out, because I didn't think that you, so have you solved problems that look like this before, is my question. No. Then why would they expect you to solve it now, is a good question. Okay, give me a sec. I'm going to read over the previous sections so that I make sure that I have, like, I'm solving this using the tools that you guys have been given. So I'm going to put the recording on pause really quick. And, okay, so I forgot to turn the recording back on, so we did some stuff. Basically, what we did was we checked the discussion board, and it turns out that the best method, well, according to the book and the discussion board, the best method for solving this would be using the graph, which we mentioned earlier. So we graphed r of t, and we used that to find the area under curve. Which was, of course, that's curve, which was, of course, negative. And the graph ended up looking something like this. And so this was the area that we were looking at. And then I went to the book because I have the answers in the book, of course. And this was the answer, but we decided that our answer based upon the graph would not be this precise. So we really said anywhere from negative 40 to like negative 45 would be like reasonable based upon like how specific this graph would have to be. So this is the answer that the book had, that was in the book, all of that jazz. And then we basically just added them to end up with our actual answer, which is 45.8 degrees Celsius. Okay, everyone's caught up now. Good. Whew. Crisis averted. I would have forgotten to turn it on. Okay. let's move on to 5.6 so we can actually get some of these problems done. And so this is talking about average values. Did you guys have any specific questions in terms of what's going on in this section?
In the book, I don't like how they do like the examples because that it's kind of confusing when you actually go to do the problem.
Mm-hmm.
So like in example 3.
Okay, example 3.
In the book, like they are taking the area under the graph of the, like it's below the actual graph.
Mm-hmm.
So it's, and then when you do the problems, it's like you have to take the area of the whole thing. So that part was kind of throwing me off.
Okay. Okay. So you're having difficulty working between the graph and what they're saying that the average value is. Do you understand, like we've been talking about algebraically versus like graphically? Do you understand the algebraic explanation of this?
Yes.
B minus A. Okay. Okay. Oh, and this is from me. Okie dokies. So, that is not, in example 3, I guess that's not really how I would have done it, but give me a hot sec. Okay, so we understand what it is. Okay, so what they're doing with the rectangle is basically they are trying to like graphically represent like the halfway point of the area, correct? So if we look at figure 5.71, so we're on page 273 right now. We have this graph that looks like this. And here is, this will be A, and this will be B. And so what they do is they have this whole thing colored in, and so this is the area under the curve, and so it goes all the way up and around. But what they want to find is the average value, and so the method that they use to do that is they get a rectangle, and the area of this rectangle is equal to the area under curve. And so you can see it perhaps a little bit better in the book because this chunk is not so tiny and this chunk is not so large, this portion right here. But basically they're like approximately equal. And so what they're trying to do is they're trying to say, so I have this space, and the best way to like represent, trying to think of a good analogy for this, maybe midpoints. So if I had a line that looked like this, and I had a point here and a point here, how would I find the midpoint? Well, I would say, for instance, this is going to be 2, 2, and this is going to be 0, 0. Where are the points? This point is 2, 2. This point is 0, 0. What is my midpoint going to be? Well, the slope of my line is going to be rise over run, so it's going to be 2 over 2. So the slope of my line is going to be 1. So the midpoint between this is going to be 1 in this direction and 1 in this direction. So this is a 0.11. So one way to do that would kind of be to like draw like these lines. So rise, 2, run, 2, rise, 1, run, 1. 2 minus 0 divided by 2. Anyway, okay. So midpoints. Try to think of like lines and midpoints. But then instead of a line, what we have is a whole area. How do we think of a whole area in terms of like that sort of strategy? Well, that's too much. That's also too much. What we're going to do is we're going to say that this area is approximately equal to this area, the area of this blue part. And so we're going to say that this whole area is, the area of the pink is equal to the area of blue. I'm going to draw that in blue. And so at this y value, that is where the average is. So conceptually, it's not the easiest thing in the world to understand, in my opinion, but like graphically representing it, but I would think of it in terms of like midpoints, but elevated, I guess. Okay, so let's do a problem or two from section 5.6. Let's do a problem or two from the focus on theory. Okay, were there any problems in particular that you had trouble with in this section, or types of problems that you would like to discuss? Number 2. Let's do it. Okay. All right, so the integral from 0 to 5 f of x dx is part A. This is what we want to find. So let's start with that, because that is going to like put us in like the position that we need to be in to solve the rest of the problem. Oops. Okay. So we have this this graph. We're going from 0 to 5. We're going to estimate the integral. Again, we're doing this using graphs, and especially when I'm writing in Zoom, my graphs are not the most precise. But this is something that you guys have done before, so I know that you guys can do it again. We have a graph that doesn't look very much like that, but that's what we're going to have to go with. Here is 1. That's, why did I draw the line like that? 1, 2, 3, 4, 5, or something like that. And so here's 0. And so it starts off. Here is 7. This will be 5. This will be 3. And this will be 1. So basically what we're going to do is we're going to estimate the area underneath this curve using these boxes. Which I think is the easiest way. So what I would do is find the dimensions of one box. So if I have one box, I go over 1 and up 1. So the area of one box is equal to 1 unit squared, because we're not really given any units or anything like that. Correct? So I'm basically just going to count, because that's what would be easiest right now. So that's 1, 2, 3. So about 26 boxes. Is that what you guys got? So the book says 25. So that's fine. Oops. The book says 25. So area is approximately equal to 25 units squared. Okay, are we cool with how I did that and what the answer is? Yes, no, maybe so. Cool. All right. So I am going to say this is problem 2. This is part A. The integral from 0 to 5 of f of x dx is equal to approximately 25. All right. So now we're going to say we need the average value between x is equal to 0 and x is equal to 5 by estimating visually by the average height. So for part B, we're going to use the graph. And then for part C, we're going to use algebra. I hope it's legible. Okay, so we have this graph. It looks something like this. Goes from 0 to 5. This is about 7. So what I would do is I would kind of we want to draw a line where the area that's in the rectangle is approximately equal to the blank area in the rectangle is approximately equal to the blank area out of the rectangle, right? So if I were to do something like this, and I drew this line at about 5, what would this look like? Well, this area is equal to approximately, oh, that's really tiny. So that's going to be like, let's call it 0.25. This area, I'm going to get a different color. This area approximately is going to be, we've got I don't know, it's not quite 2.25, I think. Let's go with 2.1. Again, this is all just kind of estimation. And so this area underneath here that is in the rectangle but not, this is going to be area is equal to 1, 2-ish. So is this area inside approximately equal, or the area inside this rectangle approximately equal to the area outside the rectangle? Or is the area inside this rectangle approximately equal to the area under the curve? Okay, what is the area under the curve? That's our integral, 25. So this would be 5 times 5, which would be approximately 25. So that makes sense. So again, these are all of these areas are estimates. So it's not exactly precise, but it's kind of reasonable to say that they're close enough. So are we cool with using the graph to do that? Did we follow what I did looking at that? Okay. Okay. Why do I draw dotted lines? They're so hard to erase. Okay. All right, let's do this using algebra. Well, our equation would be given as 1 over b minus a times quantity times the integral, excuse me, the integral from a to b f of x dx, which we know. So putting in the numbers that we want, we have 1 over 5 minus 0 times 25, because this is all equal to 25, given by what we know up there. So 1 over 5 times 25 is equal to 5. So this should be y is equal to 5. So that would be average. And given by this, y is equal to 5. Thoughts? Comments, concerns? Okay. We are running a little late. So do you want to take a look at number 5 in the focus on theory? Properties. Well, there's like a line of yeses in the chat box, and I'm never sure when each of them was sent. So I hope you said yes to the focus on theory. And just be sure to stop me at any time. Okay. Here we are, 288. Okay. We want to do number 5. So we have this that looks like f of b is equal to 0 to b, 2 to the x dx. We want, for part A, f of 0. For part B, we want to know increase or decrease. And for part C, we want f of 1, f of 2, and f of 3 estimates. Okay. So, what is the second fundamental? Sorry. Trying to kick a cold. Okay. So, second fundamental theorem of calculus is g of x is equal to a to x f of t dt. So function g is defined on this integral. Then we also know that g prime of x is equal to f of x. Okay. So using this, we are going to try to find all of the answers to number 5. In 5, x is going to be analogous to b. This big F is going to be G. I'm just trying to like make connections to these down here, because here we have B, here we have B. A is a number, so that's 0. And then F of T, So t is actually going to be x. They swap some of these variables out. It's just important that you keep track of like what's going on, dt or dx. So, okay. So a, b, and c are any numbers on continuous functions. We have a lot of, oh, these are just rules for definite integrals. Sorry, I'm looking at page 288. Okay. So, okay. How am I going to solve this? Give me a second. It's been a hot minute since I've done this. This problem's a little puzzle. Okay. Oh, okay. We're on the right track now. All right. So let's just look back at what we originally want. I got very caught up in like trying to like look at this that I didn't realize what we want is right here. So if we want f of 0, then we're going to be looking for from 0 to 0 to the x dx, correct? To the x, not 2 times x. And I want them to. So basically, it's just going to be the, like there's no interval involved. It's like the same like location, right? So if we were to, for instance, sketch this out, we have this 2 to the x, and then we're just looking at it at like a single point, but we're looking for the area under the curve, and there is no area between points. There's no distance to find area under the curve. There's no area. It's like if you have this hypothetical little rectangle that you were doing if you were doing Riemann sums, but this is 0 times like the height, and anything times 0 is going to be 0. So f of 0 is equal to 0. All right, are we on track with that? Yes, no, maybe so. Makes sense. Good. That's good. Let me erase some of this, these arrows and stuff. Okay. So, then we need to find whether or not it's increasing or decreasing. And what we want to do there is kind of, again, go back to the graph so that we can like envision what's happening. So B is getting larger. So if we have this graph, and B is getting larger. So here we have 0. This is like a fixed point right here. And B is moving from 0 and becoming larger. What's going to happen to the area under the curve? Is it going to increase or decrease? It's going to increase, because we're really going from 0 to nothing, or we're really going from nothing to something. So that is going to be an increase. Why did I get? Where's the blue? So it's going to be an increase. So we're assuming that B is greater than 0. Yes, so that makes sense. Okay. Now we're going to estimate what f of 1, f of 2, and f of 3 are going to be. So again, we want to like consider this graph. And this graph is of 2 to the x. So part 3, it's just the area under the curve evaluated at those points. You're right. So what we're going to do is say here at point 1, what's going on here? Here at point 2, what's the area look like down here? And then at point 3, what's this area look like? The whole thing. So we are basically, the book says that we want to like use a calculator or a computer to like figure out exactly what's going on here. But it is just going to be the area under the curve. So what do you think is going to be bigger? F of 3 or f of 2? F of 3, exactly. Because there's just more area under the curve. So let's say 2 to the 1. How do we best to approach this? So area under curve. Let's go back to how do they? Okay. Well, because they say use a computer or a calculator, I guess I'll just kind of like give you what's going on. So we have a 1.4. Approximately f of 2 is approximately equal to 4.3. Oh, that was wrong. 4.3, and then f of 3 is approximately equal to 10.1. So you were right, f of 3 is greater than f of 2. So everything kind of makes sense. Would they give you this problem on an exam? They would not, because you would have to use a computer or a calculator to figure it out. But that is basically this problem. So you're kind of like analyzing like what's happening to this integral as things change. Cool, I'm glad. Okay. Are there any more questions about like this material, things that you're having trouble understanding the concept of? Okay. Awesome. You guys have a great week. Email me with any questions that you might have. Yeah. Have a great day.